tutorial for the Simplified Rosetta Protein-Ligand docking workflow. So what you need for this workflow initially, all you need is a protein file that you're interested in docking, some ligand files, at least one, access to an MSU HPCC account, and final. And if you have access to an HPCC account, you also have access to HPCC on demand, and this will be our file transfer system that we'll use. So that is all you will need, no additional software dependencies. One problem that HPCC recently created of their own doing, they limited home directory memory to 100 gigabytes. Well, they're going to, starting on January 20th. Last year and years prior, you could request up to 1 terabyte for your home directory, which is what I did. But it seems that they want home directories to actually be used as home directories and research spaces to be used for intensive work. So they're actually boosting the amount of space we'll have on our research, or we'll have to request, but we can go up to 3 terabytes on our research space, but our home directories will be limited to 100 gigabytes. Anyway, this means that you probably won't be able to do docking to the extent that I've been doing it over the past few years because of these memory constraints. So this tutorial will also apply to an installation that I'll put on the Wooldring Lab research directory. Just a heads up, you can still run docking, just you probably won't be able to run it for many hundreds of ligands. You will max out your 100 gigabytes pretty quickly. And actually the default is 50 gigabytes that they give you. They're gonna move you to 100, but right now if you didn't do any like quota increase form, you probably have 50, which is almost nothing. Rosetta by itself is about 32 gigabytes, so that's going to take up the majority of your 50. And regarding like what sort of memory use docking produces, so every 13 gigabytes, there's 13 gigabytes produced for every 65 ligands using this workflow, so you probably won't be able to dock very many. For the sake of this tutorial, I'll just demonstrate 4 ligands. So initially, if you're curious about what sort of memory use you have, you log on to HPCC and you simply type the quota command. And that will tell you how much space you have. So I have 1 terabyte in my home directory. They're probably going to knock this down to 100. But it tells you how much space you have left, how much space you're currently using, and also your files quota. This is also very important. You have a memory quota and you have a files quota. So you look at your use here. So definitely check this out before installing Rosetta in your home directory with this workflow. So in total, it'll be about 36 gigs. Yeah, obviously you also need to be familiar with HPCC on demand. That's simply just log on at this link. It'll take you here, and it should prompt you to log in. You go to your home directory, and this is a very intuitive, easy to use file management system. So yeah, that's memory concerns. Okay, so actually installing Rosetta. So you can install it from my account directly into yours. You don't need to download it, compile it, because I removed all restrictions on my home directory, so anyone in IQ, and I think anyone in chems can access it. So you definitely should be able to install it from my home directory. And this is assuming you don't already have Rosetta. If you have nothing related to docking, and you want to start completely new with Rosetta and the entire workflow, this is what you need to follow. I'm going to go over how you can move an existing copy of Rosetta that you have into the workflow structure as well, so you won't need to download Rosetta again from my directory. That's obviously you don't want to add to waste an additional 32 gigs of memory from your home directory. So there's this file that I attached on Microsoft Teams called copyingjob.txt. It's shown here below. You simply upload this into your home directory. So you take the file, you go into your home directory, you upload, and you just drop it in here and it goes in there. That's how that works. The file basically that's the copy command. It will take it from where it is on mine, and it will copy it. In this case, this is the file I sent to Alex when he used it. It will copy it to yours. So what you need to do to this file before using it is change Alex's NetID here to your HPCC NetID. And that would be, if you are unfamiliar with that is, that's just that. Like whenever you type HPCC commands, whatever appears before the node you're in, that's your NetID that you would type in there, which is also the same as your MSU NetID. So yeah, what you do to run this job, you upload it in your home directory, and you type sbatch, the name of the job. So just to demonstrate that, I'm sure you all know how to do this, but you would just, yep, that's it, hit enter, and it will start running once you have it. It will take a while because if you are transferring the entire directory with Rosetta, it's 36 gigs, so you're copying a very large package. If I remember correctly, it takes about 40 to 45 minutes, so don't expect anything to happen immediately. If you have the job running, you can type the QS command, hit enter, and that will show you if it's running or not. There's nothing running now, but it will show you the job ID and it will show you when it started. And if it has an R under the ST, that means it's running. So, and if it has a PD, it's pending. But either way, it's going to submit. It's going to take approximately 40 minutes, and you're going to transfer everything from my directory with all the workflow with Rosetta into yours. So at the end, you should see a directory called streamlined_docking in your home directory once this runs. You can tell the job is finished if you type QS and then nothing appears like I just did. So if you have this, it's done. So what it will look like, I have a bunch of other directories, but you'll see something called streamlined docking in your directory when it's done. So that's how you have it. Yeah, so this applies if you do not have Rosetta in your home directory and your directory is relatively free of anything. You're sort of new to HPCC, you don't really have anything in there. You have everything you need. However, you may previously have installed Rosetta in your home directory. And in that case, you don't want to install Rosetta again. For me, that's too much memory use. So what you can do is you can copy the entire directory structure in my workflow without copying Rosetta over. So it's a slightly different command. It's shown here. You basically take all of this and you put it in the copying job file, delete what exists currently in the copying job file, put all of this, you change 2 lines, you have the CD line here, and you have this rsync line here. And again, the only thing you need to change is you need to change Alex's NetID from here to yours. Everything else remains the same. And this would be the copying job that you would use in that case, and that's going to transfer the entire directory structure without Rosetta docking. So if I go here, everything within streamlined docking except the Rosetta package. It's not going to transfer that because you already have it. Okay, so you're not done in that case. You'll also get it as streamlined docking, but your Rosetta package is going to be somewhere else in your home directory if you already have it. So you're going to have to move your Rosetta folder from wherever it is in your home directory to the newly created streamlined docking directory. So the first thing that you do in streamlined docking is you have to create a directory called Rosetta package because you did not transfer it over from my side. So you have to make a directory called Rosetta package. And now you can move your Rosetta file from wherever it is into this directory, this newly created directory called Rosetta package, which is within Streamlined Docking. There's a brief guide for using the mv command here at this link. And another detail, you're also going to want to rename your existing Rosetta folder that you had prior, if you had it, to Rosetta_312. So my script is very particular about the names and the directory organization. So you're going to want your newly named Rosetta 312 that you actually had before to be placed within this newly created Rosetta package directory, which is within Streamlined Docking. And you know you have the hierarchy right if Rosetta_312 has demos, documentation, main, and tools in it. So you see this order, you created Rosetta package, you moved your Rosetta into Rosetta package and renamed it to Rosetta_3.12, and it has these four. You're good. That means you got the order right, the script can work. So that's if you have a Rosetta installation that you want to use and you don't want to transfer all of Rosetta to your directory. So yeah, that would be that. So now that you've installed it, you are ready to begin inputting files and running it. So you go to HPCC on demand to input the files. You go to your home directory and you go into Streamlined Docking. It should look like this. You should have a list of directories and then you should have 3 Python scripts at the bottom. So the only directories that you will put inputs in are protein inputs. I already put my protein that I want to dock in there. And ligand inputs. I put those as well. Yeah, those are the only inputs you'll need. So, yep. You'll first need to obtain a PDB file of the protein. I attached the PDB file that you can use to follow along with this tutorial, the hndtest.pdb. However, the PDB file will need to be cleaned, and I'll go into that later prior to using it, and you can do that with Primal. You'll also need your ligand SDF files, which you need to be 3-dimensional conformers. They need to be 3-dimensional structures of ligands, like so. See this here? It's a 3-dimensional ligand structure. Of all the ligands you want to dock, again, you can use the ones that I attached to the tutorial. There's one directory that might cause problems in the near future. It's this BCL package directory. This is the conformer generator that Rosetta uses to sample different configurations of the ligands, because you know molecules are flexible entities and they can move, they can rotate, so it's not very accurate if you treat them as sticks that don't have joints that move. So this directory, you'll be using this to generate conformers. The problem with this one is there's a license in here that expires every year. I think it's due to expire in March of this year. I believe I actually wrote in this guide. Yeah, until March 23rd. It's going to expire on March 23rd of this year. So I'm going to need to renew it myself, but I don't know if you can simply use my license by copying my directory over. I'm pretty sure you can, but I'm not certain. So just as a precaution, you should get your own license and upload it in there. And you do that from this link, the Myler lab, because otherwise you won't be able to run the conformer generator. However, actually you can test if it works on your end simply by going into the directory and going into the BCL package directory and typing this command, the /BCL exe. And if you get this wall of text, the help menu, you're good. That means the license is still active. I believe this is the case. But anyway, around March, you should try to get a license because it'll run out on me as well. So yeah, if you really want to see the link, it's an old Myler lab site. This is a license that I got recently. And you'll go to this and you'll enter your information, operating system, and you will select molecule conformer generator for the software that you want to license. Okay, so BCL should be licensed. But yeah, as a precaution, you should try to get a license. Okay, so your protein file. For the purpose of this tutorial, you're just going to use the one I provided, but ultimately you're probably going to get them from the protein data bank, or they're going to be alpha-fold generated. If they're alpha-fold generated, they're fine. I mean, they're not fine. You're going to need to relax them, but that's beyond the scope of this tutorial. You should, however, from the protein data bank, they're not going to be clean. They're going to have a lot of cofactors, small molecules, and other stuff in there that the docking workflow cannot process. So you're going to have to clean them. So to clean them, I'll do a very quick demonstration of that. This is a random structure that I got from the PDB. To clean them first, you're going to remove the waters. So you go here, you remove the waters. You can see the waters as these red dots. You remove the waters, and you want to get rid of this molecule too. This is not the one you're going to be docking. So to do that, you go to display, sequence, and there. You go to the actions, and you remove atoms. So that, your molecule is now clean, so you want to save it as export molecule. That. And the difference here is you're not going to save it as a .zip file, you're going to save it as a PDB. And you can name it as whatever. I would keep its original name, but yep. And you save it. And once you have it cleaned, I go over all of these steps again here for cleaning it, removing waters, sequence, removing the atoms from the selected. Yeah, you just upload it into the protein inputs directory. So, I already put mine here, but yeah, you just upload it, drop it here, and it's good to go. So yeah, now the ligands, you should have the SDF files ready, the ones I provided, and you're also going to upload them into ligand inputs. Note that you are not going to upload them into these 3 directories, the ligand conformers, file, and protein ligand complexes. You're just going to upload them to ligand inputs, so they should appear alongside these, not in them. Like so. These are the 4 that I'm using. Those other directories will be filled with other files that the workflow will generate. You don't really need to mess around with that. It's fine. Okay, so the next problem is you'll need to know exactly where in the protein you will want the simulation to occur. I included a small guide within the Streamlined Docking directory. It's this directory here. It tells you to please read it. You don't really need to because I included it in this guide as well. But it's a text file, and it refers to a bunch of images, and I reproduced the whole thing here. So what you're doing is you're finding the starting coordinate of the docking, so where the molecule is going to start its movements throughout the protein. And alongside that, you're also going to define the boundaries in which it's allowed to move. So you can think of it as a cubic volume in which the molecule moves somewhat randomly throughout the simulation. And it starts at a certain location and it ends up anywhere within that volume, and its interaction is scored with the protein. So the first thing you want to do if you want to open a protein structure, this is actually the one that I will be docking. You want to toggle this menu, the selecting menu, until you reach atoms. Once you reach atoms, you can select an atom on the protein structure. So that one is selected and it will appear as a pink dot. So the next thing that you do, because you want to think like, okay, where do I want a good starting coordinate for this protein structure? I want it to start here and I want it to move throughout this whole entire transmembrane domain. So that seems like a reasonable location. And so I was like, okay, I'll use that as a starting coordinate. And the command you'll use is the following. And that will give you the X, Y, and Z coordinates respectively of the atom you just selected. Note those down. You will input them later. You don't need all of these decimal points. You can use 1 or 2 or whatever. You don't need this level of precision. So that's your starting coordinate that we're going to use. Again, this goes through that as well. Okay, so now you have to get the grid dimension. This is the only other dimension you'll need. And the grid is like, okay, I have a starting coordinate. This is the center of the cube in which the ligand will move in the simulation. What side dimension of the cube seems reasonable? So let's say I wanted to sample this entire transmembrane area. Let's measure. You can measure by clicking the M, and then you can click somewhere in the protein, and this little white dot will appear there. And if you connect it to another place, it'll measure the distance between these. So you say, okay, 40. Does that look like a good side dimension for a cube centered at that previous location? Yeah, I think that's decently large. Obviously, if you have no idea where the ligand should be on the protein, the larger the better. But in this case, this is an OATP. You know that the ligand is mostly going to move in this central cavity area. So you don't necessarily need to go as far out as these exterior helices. So 40, okay, record that as well. So you have your 2 dimensions. In this case, it was 38 in this guide, but somewhere. So now you have everything you need. You put the ligand files in ligand inputs, you put the protein files, protein file in protein inputs, and you're ready to run the script, namely Rosetta docking part 1.py. So what you're going to do is you're going to go into the streamline docking directory, and you're going to type Python part 1. And it's going to ask you for the exact protein file name that you want docked. So make sure you type it exactly as it is, and you include the extension, otherwise it will not find it. So in this case, that is the protein. It will tell you that it found it. Now it's going to ask you if you placed the ligands in the ligand inputs directory. If you say no, the script is just going to not do anything. You're going to have to run it over. So you're going to want to put your files in there, obviously, to get it to run. And if you say yes, but they're also not there, it's also going to say that it didn't find anything. So you can't. The script has a bunch of comprehensive checks in place to make sure that you actually have the files ready, and you can't just fool your way through it. And yes, I did. So it will tell you the ligand files that it found in ligand inputs, and these are indeed the ones that I input into it. And it's going to tell you that conformer files and protein ligand complex files are missing. This is perfectly normal because these are completely new ligands, and I did not process them at all. The script will generate a Slurm job that will take care of generating these conformer files and these protein ligand complexes. So for you, when you run it with completely new ligands and a completely new protein, of course you're not going to have these files. So it's going to generate this job to address that problem, and it gives you instructions on exactly what to do. The job is generated, so all you need to do is type this command, the sbatch conformer params concatenation job.txt, which is the file that is generated. So the script is designed to be pretty foolproof. If it doesn't continue executing or something, it didn't do anything wrong. You're the one that probably screwed up. You didn't input a file somewhere or something like that. So the script has a bunch of checks in place. Now we're actually going to run this job because I deleted all of my conformer and protein ligand complexes. So it's going to run, and this is an example of job submission and QS command, as you can see here. The job started, you can see the status it's running, and it shouldn't take very long for 4 ligands. The conformer generation, I've had it take 15 minutes if I was running like 60 or something ligands, but that's not the case here. I'm running 4. So this is how you monitor progress, and eventually it's nothing's going to show up there anymore. And what you do when this job stops running, you simply type Python Rosetta docking part 1.py again to run it again, and the script will know that now you have the files because it will check the directories where the complexes and the conformers are supposed to be, and it's going to see that indeed they are there now. So it's not going to let you go on without having these files. So what you're going to get next is this. It's going to ask you to type in the name of your protein again, and whether or not you input ligands, and it's going to see that indeed you did generate the conformers and the complex files for the ligands, and it's going to then ask you if you want to perform local docking or global docking. So I should finish by, I think one of the molecules that I put in is quite large, so that might be the reason why. Yeah, so it's always going to check for missing ligand conformer and protein ligand files whenever you run it. So, okay, it finished. This is what a job looks like when it's done. When you type QS, you don't see anything in there. So now you run the script again. It's going to ask for the name. There we go. Indeed, it's there. Yes, I did. And now it's going to say that it found the ligands, and it's also going to tell that all the ligands that are in there have conformer and protein ligand complex files. Now it's going to ask if you want to perform global or local docking. So I haven't added the section for doing global docking. It's going to be a little more involved, but local docking is the only option. If you do global, it's not available. Just going to tell you that. So, oh, and another thing, anytime the script ends like that and it doesn't continue, just run it again, and we'll start from the beginning. But this time it will know that you have you've generated the conformers and the protein ligand files. So nothing, you didn't screw up anything if the script stopped running. Just run it from the beginning. There's only a few inputs you need to do again. So yeah, now it's local. And now it's going to ask you if you're ready to provide the starting coordinates that you determined and the grid dimension. So that's why I say you should have noted those and say yes. So let's just use the ones that the guide provided. Grid dimension of 38, and let's just use these. So you just need to type them exactly as they are written here. You can use more than one decimal place, or you can use just one. That doesn't matter. But you need to space them as opposed to using commas. So you have that. And the grid dimension, let's use 35. Okay, so This created all of the files that you're going to need for the docking. It created the XML file, which contains the coordinates and some of the score function weights that the docking is going to use. It created the options files, which tells Rosetta where all of the files that it needs are, and it also tells Rosetta what main score function to use. And it created the docking job files, which are actually the files that you're going to run to execute the docking. So these are all of the files you're going to need. And it also tells you, it gives you some instructions at the end. So in our case, we only have 4 docking jobs for 4 ligands. These can just be submitted one by one if you want to start the docking now. Since you only have 4 and it's not too onerous to type 4 commands of the type like that. You just type that one, submit it, wait for it to submit, next one, onto the 4th one. However, if you're doing extensive docking, there's going to be cases in which you have hundreds of ligands potentially. And you're not going to want to type sbatch, the name of each individual file, for hundreds of ligands. That's going to be extremely inconvenient. That's why the Rosetta docking part 2 script exists. So that's, for the sake of this demonstration, I'm going to run Rosetta docking part 2 so you can see it in action. But the main purpose of that one is if you have a bunch of files, that's what you use to generate what are called batch jobs, which will submit many different docking jobs simultaneously. In this case, it submits a maximum of 65 of these simultaneously. So that's what you're going to run if you have hundreds of ligands you want to dock. So it also notifies you that it generates a docking job file for every ligand that you had in ligand inputs. So if you should make sure that the ligands you have in the ligand inputs directory are the ones that you want to dock, because by default it docks all of those. So it just emphasizes that. So yeah, you can submit them now if you have a few of them, but we're going to run the part 2. But if you were to run them, where they're going to go into a folder in the docking results directory within Streamline Docking, which was named after your protein. So this directory appeared, it was generated by the script, and all of your docking results are going to go in here. And your docking results are going to basically be PDB files of complexes, and a score file that gives the interface energy and a bunch of other terms. So there's going to be another video in the relatively near future on how to process the docking data. So yeah, that's that one. Yeah, so we're going to run part 2 because we generated the docking files, even though we don't need to. So part 2, it will ask you if you ran part 1. Even if you say yes, but you don't have any docking job files that are generated, it's not going to do anything. Another check to ensure that you can't fat finger your way through it. Yes, I did run it. It's also going to ask for the name in order so that it identifies the docking files. It's going to say that indeed the protein exists, and these are the files that are associated with it. So how it creates the files, it puts a maximum of 65 in each batch submission job. So say if you have the example the guide gives is if you have 175, the first 65 will go into one, the next 65 will go into the second one, and then the remaining 45 will go into the third. So we'll create 3 batch submission jobs, and they will be what you run. So if you ls now, you will see a batch submission job that was generated. This is the one that contains all of these, and if you want to see it, you can see it S-batches all of them for you. So that's the purpose of this. Yep, so let's actually S-batch it. Yep, so now it's running. These usually take a while to submit. Oh, no, it ran. So what you're going to see is this is the job that initializes the submissions of the others, but as you QS it, it's going to add the other docking jobs to this list. So this is just the batch job, but it's going to add the other docking files. Yep, you can see all 4 of them here now. Yeah, and then if you have more, you're obviously going to see a wall of docking jobs. And if you want to cancel any of them, just let them run a little so we have one input to look at, or one output to look at. If you want to cancel them, you just type scancel and then the ID of the job. Yeah, it's just leave 2. Yep, okay. So, you executed part 2. Okay, so regarding time, docking takes time. If you have a batch job of 65 ligand files, that's going to take a full day, around 24 hours to both submit and finish running. Again, this is going to add about 13. This is going to take about 13 gigabytes of memory for your home directory. So consider how much space you have, check the quota, and see if you're able to do this. For 4, you should have no problem doing this exercise. But yeah, it takes time. For hundreds of ligands, several days is normal. Another thing, yeah, if you run QS, you might see not applicable and start time. This just means Slurm hasn't loaded your job yet. It doesn't mean that it canceled your job or anything. So, yep. So this is again another example of the. Okay, so this. You're running jobs. Let's say you are done running your docking jobs. You've submitted all batch files that you intended to run. And you've noticed that you've begun accumulating these files, Slurm files, which just indicate they're your tickets, basically. You submitted a Slurm job and you get this ticket out. And you're accumulating docking jobs. You should keep the space pretty tidy if you want to keep track of what you need to do. So there's this other script in here called directory custodian. It's just a very simple, you enter it. It's just going to ask if you finished. It's going to ask if you finished because it's also going to delete the docking jobs. So maybe you don't want to delete those. Maybe you want to do those again. But in this case, we're going to say we did finish it. So it deleted all of the files within Streamline Docking, all of the docking files, all of the Slurm files. It deleted all of the options files, so those will need to be generated again for a new docking. It deleted the XML file. However, it did not delete the ligand SDF files and ligand inputs because the assumption is you're probably going to dock those again, either against the same protein or a different protein. But if you don't, you should delete those on your own. So yeah, this is the purpose of that script. Yeah, now we should have some inputs, or outputs rather, docking outputs, just so I can quickly show you what that would look like. All right. So, yep, you can see them all canceled. Okay, so regarding what outputs are going to look like, we're going to go in here. So you go into Streamline Docking, docking results, and you can see it's going to have the ligand name, the protein name, this is a different ligand, and it's going to generate up to 1,000. So perhaps later I'm going to mention how you can generate less than 1,000, you might only need 500, but 1,000 is sort of the standard for docking. If you want to perform a thorough docking, you usually generate at least 1,000 poses. So, yeah, it's just a protein complex. And at the very end, you get a score file for each of the ligands, which will tabulate the binding affinity between the ligand and the protein in each of these different poses and other metrics. So that will come in a future video. Yeah, I don't actually care about the score file. Let's just get what will this look like? Show you what an output will look like. Okay, here it is. So you can see. Okay, so my coordinates. This one is actually. Oh yeah, the ligand is tiny. This is probably a bad one. Let's see the other ones. Okay, so you can see the ligand and you can see the protein. In this case, the ligand is way outside the protein, but that's because the coordinate that I put in was a really bad coordinate. So I used the coordinate not for this file, but for the example file from the guide. I should have used the coordinate for this file instead to actually place it in the center. So one thing to keep in mind is you really do have to check the starting coordinate for your protein file manually, because the same protein file might have completely different coordinates. So yeah, but this is what it will look like, except instead of being here, ideally it will be there. But yeah, that's a complex. So yeah, that's what you get. Those will finish running. And yeah, that's how you run the scripts. This guide contains basically everything I said and more, so feel free to refer to it if this video wasn't helpful enough by its own.